All right, welcome back everyone to the deep dive. You know how this works. Give us the source material and we'll break it down, analyze it, and bring you the key insights that'll make you the smartest person at your next dinner party.
And tonight, we're continuing our exploration of ancient Indian astronomy with a deep dive into one of the most pivotal and influential texts in that tradition.
That's right, we're talking about Aryabhata's Aryabhatiyam, specifically verse 4.
Now, if you recall from our last deep dive, we were absolutely blown away by the sheer cosmic scale presented in verse 3. Those mind-boggling numbers, those vast cycles of time, those countless revolutions of planets across eons. It painted a picture of a universe so immense that it was almost difficult to grasp.
Absolutely. And in a sense, that's exactly what verse 3 was intended to do, give us that sense of awe and wonder at the vastness of the cosmos. But here's the thing. As incredible as that grand cosmic vision is, it doesn't tell us much about what's happening right here, right now.
Exactly. It's like having a giant clock with all these intricate gears and mechanisms, but no hands to actually tell you the time.
You know, it's like knowing that a river flows for thousands of miles, but having no idea where the bridges are.
That's a great analogy. And that's precisely where verse 4 comes in. It takes that grand cosmic clock from verse 3 and gives us the tools to actually read it, to make precise predictions about the movements of celestial bodies.
So it's like verse 3 establishes the cosmic playing field, and verse 4 gives us the rule book and the referee to make sense of the game.
I like that. And for all of you listening, what you'll gain from today's deep dive is a clearer understanding of how ancient astronomers like Aryabhata moved beyond broad cosmic concepts to the intricate details of astronomical calculation and forecasting. You'll see how they took those vast cycles of time and anchored them in a way that allowed them to predict the positions of planets with remarkable accuracy.
So to really appreciate the brilliance of verse 4, we need to set the scene a little bit. Imagine, if you will, that it's the year 499 CE. The Gupta Empire is at its zenith, a golden age of art, science, and culture. And in the intellectual heart of that empire, a bustling city called Kusumapura, there lived a brilliant mathematician and astronomer named Aryabhata.
And he's observing that same night sky that we see today, but without any of our modern telescopes, computers, or understanding of astrophysics. They only had their keen observations, mathematical ingenuity, and a profound reverence for the cosmic order.
And they had this incredible concept of the Mahayuga, this vast cycle of time spanning billions of years that encompasses the creation and destruction of the universe. Verse 3 gave them these mind-boggling numbers: 4.32 million revolutions of the sun, 57,753,336 revolutions of the moon, and so on, all within this massive Mahayuga. But just knowing those huge numbers, those long-term averages, how do you actually use that information to figure out where the sun will be tonight or when the next lunar eclipse will occur? That's the incredible challenge that verse 4 helps overcome.
It's a brilliant shift in focus, isn't it? Verse 3 paints this grand picture of cosmic time, the big cycles, the long-term averages. But verse 4 zooms in, providing specific markers, parameters that allow for a much more granular understanding of how celestial bodies are moving. It's that granular detail that makes prediction possible.
Yeah, I keep coming back to this bridge analogy. It's like verse 3 tells you how many cars cross a bridge in a year. It's an enormous number, a measure of the overall flow.
Yeah.
But verse 4 is what adds the lane markings, the specific entry and exit points. It's what tells you the speed limits, the timings of the traffic signals. And most importantly, it tells you the exact date and time the bridge was open for use. It's about moving from grasping that overall flow of events to actually predicting where individual cars will be at a particular moment. It's like cosmic awe meets cosmic accuracy.
I love that cosmic awe meets cosmic accuracy. And it's that drive for accuracy that really lies at the heart of astronomical prediction. It's about taking those vast cycles of time and anchoring them to something specific, something measurable, something that allows you to say, okay, on this date, at this time, this planet will be in this precise location in the sky.
And to achieve that level of accuracy, you need a set of incredibly precise calibration tools. Which is exactly what verse 4 provides.
Yes, and what's fascinating is that it achieves this level of precision even within the context of a geocentric model of the universe, a model that places the Earth at the center. But despite that now outdated understanding of the cosmos, the mathematical ingenuity on display in verse 4 is truly remarkable.
Absolutely. So what are some of these key calibration tools that verse 4 provides? Well, our sources highlight a couple of really important concepts: apogees, which is called ucca in Sanskrit, and nodes, or pāta. Let's start with apogee. The verse specifically mentions the moon's apogee, known as Candroka in Sanskrit, and gives us this enormous number, around 488,219 revolutions of the moon's apogee within a Mahayuga. Now, some scholarly estimates differ slightly on that exact figure, but it's the scale that's important here. What does this tell us about the moon's movement, and why is it significant?
Well, if we remember that celestial orbits aren't perfect circles, they're actually elliptical, then the apogee becomes really important. It's that point in the elliptical path where a celestial body is furthest away from the Earth. So for the moon, the apogee is the point where it's at its greatest distance from us. And because of this elliptical shape, the moon's speed isn't constant. It moves a bit slower when it's farther away at apogee and speeds up as it gets closer to Earth.
Ah, I see. So by tracking the movement of the apogee, this high point in the moon's orbit, you can then make adjustments to your calculations to account for these variations in speed. It's like knowing where the slow lanes are on our cosmic highway.
Exactly. It's all about refinement. Aryabhata recognized that just knowing the average speed of the moon across its entire journey wasn't enough. By understanding how the moon's apogee itself moves through the vast cycles of time, he could introduce finer corrections to predict the moon's actual location at any given time.
So apogee helps refine speed calculations. That makes sense. But what about nodes, those pāta we mentioned earlier? I know they're crucial for understanding eclipses. Can you break that down for us?
Absolutely. Picture the sun's path across the sky as we see it from Earth. We call this the ecliptic. Now, the moon's orbital path isn't perfectly aligned with the ecliptic. It's tilted at a slight angle. And the nodes are those 2 points where the moon's orbital path intersects with the ecliptic plane. Now, these interception points are critical because solar and lunar eclipses can only occur when the sun, earth, and moon are all aligned near one of these nodes.
So it's like knowing where two highways intersect. If you want to witness a cosmic pileup, you got to know where those celestial bodies are going to meet. And verse 4 tells us how the moon's ascending node is moving something like 232,226 revolutions in a Mahayuga. It also says that it's moving in a retrograde motion, or viloma in Sanskrit. What does that mean, and why is it moving backwards like that?
That's a great question. That retrograde motion, that movement against the general flow of planetary movement, is reflecting a slow precession, a kind of wobble, in the moon's orbital plane. Imagine you have a hula hoop, and it's tilted at an angle. Now imagine the points where that hoop intersects a flat plate slowly rotating around the center. You'd see those intersection points slowly shifting over time. That's analogous to what's happening with the precession of the moon's nodes along the ecliptic.
So it's a gradual drift.
Yes, very gradual. It takes about 18.6 years for those nodes to complete one full cycle of precession along the ecliptic. But knowing this intricate detail was essential for Aryabhata to make those incredibly accurate predictions about when and where eclipses were likely to occur. And given the immense cultural significance of eclipses in ancient times, this was incredibly valuable knowledge.
I can only imagine how much weight those predictions would have carried. People must have been in awe of his abilities.
Absolutely, and keep in mind that eclipses, both solar and lunar, were often seen as omens, as celestial signals of significant events. Being able to predict them with accuracy would have conferred immense prestige and authority.
It's like he's cracking the code of the cosmos.
Exactly. And our sources emphasize just how significant this shift was, moving away from purely mythological explanations of these celestial phenomena toward a more mathematically grounded understanding.
Now, another thing that struck me as I was digging through the material on verse 4 is that it includes revolution counts for Mercury and Venus, which, if you remember, weren't mentioned in verse 3 at all.
Yeah.
Why is this inclusion significant?
I think it speaks to the level of detail and refinement that Aryabhata was working with. Remember, synodic periods tell you how long it takes a planet to return to the same position relative to the sun as seen from Earth. But sidereal revolutions, which are what verse 4 provides for Mercury and Venus, are a bit different. They track the planet's actual journey around the sun against the backdrop of the fixed stars. So it's a more fundamental, more precise measure of their true orbital periods.
So he's adding another layer of accuracy to his model.
Precisely. By including those sidereal revolution counts, Aryabhata was building a more robust, more comprehensive framework for understanding planetary motion.
It's like he's building a high-performance engine for the cosmos.
I like that analogy. And speaking of engines, there's another fascinating point in our material. It seems that for the sun and the outer planets, Mars, Jupiter, and Saturn, their apogees are treated as relatively fixed in this particular verse. Why simplify things for those celestial bodies?
That's a good question. maybe it was just a matter of practicality.
That's likely part of it. Maybe those variations in apogee weren't as critical for the kinds of predictions he was focused on. Or perhaps the computational tools available at the time made those more intricate calculations extremely challenging. Remember, they didn't have calculators or computers back then.
Right, of course. It's easy to forget that sometimes.
So it could have been a deliberate choice. Prioritize the moon and the inner planets, whose positions were perhaps more immediately relevant for things like calendars and eclipse predictions, and work with a slightly simplified model for the outer planets.
So like a good engineer, he's making smart compromises to create a system that's both functional and reasonably accurate given the tools he had available.
Precisely. And the result is a system that was incredibly advanced for its time.
Okay, so verse 4 provides all these crucial celestial calibration points, apogees, nodes, revolution counts. But how do you actually anchor those cyclical movements in the vastness of time? We're talking about millions upon millions of years. How do you even begin to make sense of time on that scale? That's where the concept of the Lanka Dawn comes into play. And it's truly a brilliant idea.
It is a pivotal idea. Essentially, the Lanka Dawn is Aryabhata's epoch, his cosmic year zero. It's the fixed starting point for his entire astronomical system. And the relevant Sanskrit line from the Aryabhatiya is Bhutani Ajaka Agat Prafatakra.
Okay, let's break that down. First, we have Lanka. Our sources tell us that this was most likely Aryabhata's prime meridian, his 0-degree longitude, probably located near the city of Ujjain, a renowned center of astronomical study in ancient India.
Yes, and then we have Ajarka Yoga, which refers to the conjunction of Aries and the Sun. This conjunction marks the vernal equinox, that point in the year when day and night are of equal length, and it serves as a fundamental celestial marker, a 0-degree point in the zodiac.
And finally, we have Bhutani Wednesday, which is traditionally associated with the planet Mercury. So we have a very specific location, Lanka, a very specific celestial event, the vernal equinox, and a very specific day of the week, Wednesday. It's like setting all the cosmic clocks to a very precise moment in both space and time.
Exactly. And this Lanka Dawn, this cosmic starting point, is then further pinpointed in verse 5 of the Aryabhatiya, which helps us to date it to a very specific day, sunrise at Lanka on February 18th, 3102 BCE.
And that date holds even more significance because it's traditionally recognized as the beginning of the Kali Yuga, the current epoch in Hindu cosmology.
Precisely. Choosing this widely recognized epoch wasn't just an arbitrary decision. It provided a shared temporal reference point that other astronomers could understand and utilize, fostering a sense of continuity and enabling future refinements of his calculations.
So it's like he's saying, okay, this is where we start counting from. This is our cosmic reset button. But there's a bit of a historical discrepancy, isn't there? Our sources mention that, according to modern calculations, February 18th, 3102 BCE, was actually a Friday, not a Wednesday.
Yes, that's a point of ongoing debate among scholars. There are a number of possible explanations. There could be subtle nuances in the ancient calendrical systems that we don't fully understand, or perhaps there were symbolic or astrological reasons for choosing Wednesday specifically. It's also possible that the astronomical tables used for those retrospective calculations by later scholars were slightly different from those used by Aryabhata.
It's a fascinating puzzle.
It is. But regardless of the exact day of the week, the critical point is the significance of 3102 BCE as the foundational epoch for his system. That's the anchor for his entire astronomical model.
So why is this idea of a fixed epoch so crucial? Why not just give the cyclical periods and call it a day?
Because without a defined starting point, those cycles are essentially meaningless. Imagine knowing that a runner completes a lap around a track every 60 seconds. That information alone doesn't tell you where they are on the track at any given moment. You need to know when they started running to actually pinpoint their location. The Lanka Dawn is that starting point for all the planetary movements in Aryabhata's system.
So it's like saying, okay, the runner started at the starting line at exactly 10:00 a.m. Now we can use our knowledge of their lap time to figure out where they'll be at 10.05, 10.10, and so on.
Precisely. And the Lanka Dawn allows you to do the same thing for the planets. By knowing how much time has elapsed since that epoch, you can then use the revolution counts from verse 3 and the other parameters from verse 4 to calculate the current positions of the planets in the sky.
Okay, I'm starting to see how all the pieces fit together now. We've got the cosmic cycles from verse 3, the celestial calibration points from verse 4, and now this fixed starting point in the form of the Lanka Dawn. But how do you actually put all of this together? How do you translate those vast cycles of time into actual usable calculations? Our sources mention something called the rule of 3, or trairāśika in Sanskrit.
Yes, the rule of three is a fundamental mathematical tool that was incredibly important in ancient Indian mathematics, and Aryabhata used it brilliantly to unlock the complexities of planetary motion. It's actually a pretty simple concept based on the idea of proportionality. If you know three quantities and the relationship between them, you can use that information to determine a fourth, unknown quantity.
Okay, so it's about relationships between numbers.
Exactly. And the general formula for the rule of three is x equals a times c, all divided by b, where a, b, and c are your known quantities, and x is the unknown quantity you're trying to solve for.
I'm a bit of a visual learner. Can you give us a simplified example of how this would work in practice? Let's say we want to calculate the mean position of Jupiter after a certain number of days have passed since the Lanka Dawn. What information do we need to get started?
All right, so we need to know a few key pieces of data. First, we need to know the total number of civil days in a Mahayuga, which is approximately 1.58 billion, and later specified more precisely as 1,577,917,500 days.
Okay, 1.58 billion days. Got it. What else?
We also need to know the total number of Jupiter's revolutions within that same Mahayuga. And if you remember from verse 3, that number is 364,224 revolutions.
Right. So in 1.58 billion days, Jupiter completes 364,224 trips around the sun.
Exactly. And the last piece of information we need is the specific time period we're interested in calculating. Let's say, for the sake of this example, that we want to know Jupiter's mean position after 1,000 days.
Okay, so 1,000 days after the Lanka Dawn.
Right. So now we have our three known quantities, the total number of days in a Mahayuga B, the number of Jupiter's revolutions in a Mahayuga, and our specific time period, C, and we want to solve for the number of revolutions Jupiter completes in those 1,000 days.
So how do we set up the rule of three to solve for x?
Well, we know that in 1,577,917,500 days, Jupiter completes 364,224 revolutions. So we can set up a proportion. If we let x represent the number of revolutions Jupiter completes in 1,000 days, we can write the equation. X 1,000 equals 364,224, 1,577,917,500.
Okay, I'm following so far.
Now, to solve for x, we just need to rearrange the equation, which gives us x equals 364,224 times 1,000, all divided by 1,577,917,500. And if we crunch those numbers, we get approximately 0.23 revolutions.
So in 1,000 days, Jupiter would have completed roughly 0.23 of a full revolution around the sun. But how do we translate that into a position in the sky, something we can actually visualize?
That's a great question. We know that one complete revolution corresponds to 360 degrees. So to convert our answer into degrees, we just multiply 0.23 revolutions by 360 degrees, which gives us approximately 83 degrees. So after 1,000 days, Jupiter would have moved, on average, about 83 degrees along its orbit.
You're careful to say that that's the mean position. Why is that distinction important?
Because that 83-degree figure is based on the average speed of Jupiter across its entire orbit. But remember, because the orbit is elliptical, the actual speed of the planet varies. So the mean position is just a starting point. It's a good approximation. But to get a truly accurate prediction, we need to factor in the apogee and other variables that account for that elliptical shape.
So it's like our initial calculation gives us the scheduled arrival time for our cosmic train, but to know exactly when it pulls into the station, we need to account for things like track conditions, speed limits, and so on.
I love that analogy. And in Aryabhata's system, those finer adjustments, those corrections for the elliptical nature of the orbit, are based on concepts that are a bit too complex to delve into here. But the important thing is that by combining the mean position calculated using the rule of three with those additional corrections, Aryabhata could arrive at a much more precise prediction of where a planet would be at a given time.
It's truly remarkable. And it highlights the incredible ingenuity of Aryabhata's system. It's not just a collection of random numbers and cycles. It's a carefully constructed framework that takes these vast, seemingly incomprehensible cosmic movements and makes them calculable, predictable.
It is a testament to the power of human observation, mathematical ingenuity, and the desire to understand the workings of the universe.
And the implications of this newfound ability to predict celestial events were profound.
Absolutely. It led to more accurate calendars for agriculture, religious observances, and of course those all-important predictions of eclipses, which, as we discussed, carried immense cultural and even political weight. And later commentators on Aryabhata's work, they saw this remarkable mathematical precision as a reflection of an inherent divine order within the cosmos itself.
The precision wasn't just impressive, it was evidence of something much greater.
Exactly. And for us, whether our appreciation stems from an engineering perspective, where we marvel at this robust and ingenious framework he built, or a linguistic perspective, admiring how elegantly and concisely these ideas are encoded in Sanskrit verse, or even just from a modern intellectual standpoint, recognizing the brilliance of it all, verse 4 stands as a pivotal piece of the Aryabhatiya.
Absolutely. It takes the grand cosmic cycles of verse 3 and grounds them in this calculable, predictable reality, giving us the precision that is the hallmark of a true predictive astronomical system.
Well said. It truly anchors the entire work.
So just to recap our deep dive into verse 4, we've explored how it refines our understanding of celestial orbits to those incredibly important concepts of apogees and nodes. We've examined the significance of the Lanka Dawn epoch, that cosmic year zero that anchors all these calculations, and we've touched upon the fundamental role of the rule of three, that elegant mathematical tool that allows us to translate those vast cosmic cycles into specific planetary positions in the sky.
And in our next deep dive, we'll turn our attention to verse 5 of the Aryabhatiya, exploring how Aryabhata actually went about counting the passage of time since that all-important Lanka Dawn.
Yeah, we'll see how he brings those calculations even closer to his own present day and lays the foundation for an astronomical system that continues to resonate even today. It's pretty incredible, isn't it? To think that these ideas, conceived so long ago, still have relevance for our modern understanding of the cosmos. It really makes you appreciate the enduring power of human curiosity and the brilliance of those ancient minds who dared to unravel the mysteries of the universe.
It truly is remarkable.
And as you go about your week, think about those crucial crossing points, those pāta, not just in the celestial sphere, but also in the journey of your own life. Where do different paths intersect, and what significant events tend to occur at those junctures? Share your thoughts with us online. We'd love to hear your perspectives.
Yes, we love hearing from you.
And don't forget to subscribe to the Deep Dive so you don't miss our next exploration into the enduring wisdom of Aryabhata. This is Host Speaker's Name, signing off for the Deep Dive.
See you next time.